Now we have looked at noise, how to describe noise using spectral density, autocorrelation, etc., as well as noise models for the commonly used circuit elements like the resistor, MOS transistor and the bipolar transistor. We also saw how to calculate the noise in a circuit that contains many of these components, and finally how to equivalently represent the circuit noise. Okay, that is, you can represent the circuit, all the effect of the circuit noise by two sources at the input, a voltage source and a current source. Of course, they will be correlated, which makes calculations a little messy, but in a lot of cases you can, one of the two sources will have a dominant effect and you can use only one source to represent the noise. Okay? Any questions from anything we have discussed this far? Okay, again we'll continue with a few more concepts related to noise before we get back to the actual business of serial communication links. Okay? So one of those is sampling the noise. Okay? That is, I will show this as an example, but it can be anything. So let's say you had a low pass filter, which is a representative of any circuit, and then you sample this. Okay? So let's say this is V0. V0 of t, and you sample this at some periodically with some interval Ts, and you get some samples here, okay, which are V0 of nTs. This is a representation of the sampler implementation I am not getting into now, but essentially I am looking at samples of this V0 of t and what will be the spectral density of the sample noise. The context for this is the sampling is quite common in many circuits. First of all, we have a lot of links that essentially take the signal, sample and digitize the signal, and then work with the digitized signals. All the algorithms that you want to implement will work from the sampled digitized signals. Okay? So you need to understand what happens if there is noise at the input and then you sample it, what happens to the spectral density, etc., etc. Okay? So we have V0 which is noisy. So let's say the input is 0. We are only looking at noise now. You know what happens when a signal is sampled, right? What happens? So if you take the Fourier transform of the signal, or basically the spectrum of the signal, and then you the spectrum of the sample signal will have copies at integer multiples of the sampling rate. Okay? So now you have a noise n, some noise here, and then let's say you sample it periodically. Okay? So you get the noise samples. Just like continuous time signals have some power spectral density, discrete time signals also have some power spectral density, which is properly defined, which is in the handout that I think I have shared on Moodle. So we want to know how the sample signal is related to the original continuous time signal. I mean, in this case, the signal being noise actually. Okay. So what happens? What are the quantities we use to describe noise? What's that? Power spectral density, then variance. Okay. So how is the variance of this discrete time signal related to the variance of the continuous time signal? So again, variance means, what is variance? It is average over the ensemble, right? So imagine like a lot of instances of the continuous time noise process, and each one is sampled, you get lots of instances of the discrete time signal. So you take the variance here, you take the variance there. How are they related? They will be obviously the same, okay, because you are simply taking, in case of discrete time signal, you are only looking at variance at certain points. But again, we are looking at stationary noise and so on, variance everywhere was the same. So the variance of the sample noise is exactly same as variance of the continuous time noise that you sampled, okay. This is fine. And in fact, we will use this to, when you do all the sampling and so on, we work with voltages and with some frequency axis, etc. It's very important to get the scaling factors everywhere correct. So in fact, we will use this fact later, okay. Then, so variance will be the same, okay. Or I will simply write it as these two having the same variance, okay. So what next? What do you expect for the power spectral density? What do you think will happen? Huh? What will the power spectral density of the discrete time, I mean the sample noise look like? Yeah, so we will use hertz. So again, by the way, so let me look at let me show just one side of the frequency axis. Okay, so let's say this is the power spectral density of the continuous time signal. Let's say it is like that, okay. Now, the power spectral density of the discrete time signal sometimes is plotted with respect to the absolute frequency f, that is, and then maybe you will have fs, 2fs and so on. What I mean is the x-axis is marked in hertz. Alternatively, you can use the normalized frequency, let's say nu, and then you will have essentially 0, 1, 2, etc. Nu is basically f by fs, that's all. Both are used, okay. So now on either of these, tell me what the, so I sample this noise, okay, this x of t, whatever it was, I sample it, continuous time signal x of t, and this is what is sampled. What will the spectral density of this look like? Firstly, it will have copies, right, at integer multiples of fs. So fine, you will have this, and you will have another copy here, and another copy here, and so on. Okay? Is that correct? Huh? Multiplied by 1 by t. Why? Yeah, so what should it be to preserve the energy? Tell me. What is the energy of this? I mean, we are now talking about power, right? These are all like power signals. What is the power of the signal x of t? I mean, how do I get this from this plot? It's the area under this. Okay, and what is the area under this? This is, I mean, when I say power, it is the variance, right? Okay, and of course, we always assume ergodic stuff, so it's also the mean square value. Okay, again, zero mean is assumed here. So now, in a discrete time, in the sampled case, how do you get the power? So you have to integrate from, so in the continuous time case you have to integrate from minus infinity to infinity, and in the sample case you have to integrate from minus fs by 2 to fs by 2. Or if it is single sided the spectral density, in the continuous time case 0 to infinity, and in the discrete time case 0 to fs by 2. Okay. So what should the area of this be? What should be that area? It should also be sigma x square. So let's say the value at f equal to 0, this is s naught for the continuous time case. What should be the value here? The way I have drawn it, what should be the value? Same, it should be the same, because I have plotted the spectral density against f. Okay. So this should be s naught. Okay. For instance, just to make it more concrete, if this s naught, this is volt square per hertz, and this will also be s naught volt square per hertz. And if I plot it versus this relative frequency nu, f by fs, normalized frequency, what will that be? What will the spectral density look like? It basically, the shape of course remains exactly the same. Okay. Right? Okay. What will be this value at nu equal to 0? To get the same area, it should be multiplied by? Huh? What should be the area under this? Again, sigma x square. Okay. Area should be sigma x square. So what should be the value here? Huh? F naught times S naught. So what will be the unit of this? Volt square. And it makes sense. I mean, this is not volt square per hertz. The x-axis is not hertz. It's a dimensionless frequency. So this is volt square. So, I mean, this is again some basic stuff that you know, but get the scaling factors right in different cases, because things may be plotted even for discrete time signals with frequency in hertz or with normalized frequency, etc. I mean, normally I don't use radians per second, but it is also sometimes used. Then you will get another like 2 pi factor somewhere. So those things all have to be carefully done if you want to get the absolute numbers correct. And this is very important when you model noise. That's one of the difficult things in that, especially when you start simulating. In simulation, everything is discrete time. I mean, there is no continuous time. A continuous time is approximated by maybe a discrete time stuff with very high sampling rate. Okay. And when you calculate all these things, you have to be quite careful to get all the scaling factors correct. Okay. Anything, I mean, single-sided versus double-sided can give you factors of 2 here and there. I mean, you may have assumed something here, something else there, and similarly, hertz versus radians per second will give you 2 pi, and similarly, normalized frequency versus absolute frequency will give you a factor of the sampling rate and so on. Okay. Is it fine? No, I mean, that's the way I have written it for this. We'll see what happens if that's not the case. Okay. There is no guarantee that that will happen. So the way I have shown it, any other questions about this? This is quite simple. So all of that happens is that the spectral density will get replicated around Fs. I mean, this is just the standard aliasing that happens when you sample anything. And then depending on how you plot it, you may have to apply some scaling factor. The area from minus fs by 2 to fs by 2 should be the same as the variance. That is for sure. Okay. In fact, that fact you can use to make sure that to cross check your results and so on. So now I assume something. First of all, this is an RC filter. So what will be the noise spectral density here due to this resistor alone? I mean, let's say this is all the circuit we have. What will be this? No, what is the spectral density? Not the variance. What does the spectral density look like? It will be low pass and it looks something like that. Okay. What is the DC value? 4 kT R. 4 kT R, right? That is the value at zero frequency. And this, by the way, is the single-sided spectral density, not the double-sided one. So now the way I have drawn this picture is as though the sampling frequency lies somewhere over here. Okay. So when this gets replicated, aliasing is minimal. There will always be aliasing because this doesn't, the spectral density doesn't go to zero even, I mean it goes to zero only at infinite frequency, right? But that is negligible because it drops off. Okay. Is this fine? Now what do you think happens if I choose the sampling frequency to be somewhere here? Huh? Overlap. So can you sketch the spectral density? What you finally want is the spectral density from minus fs by 2 to fs by 2, right, or 0 to fs by 2, right, because for a discrete time stuff you know that the same thing is replicated. Okay, so what's the result? It will be the same? Huh? It won't simply add? Why? Okay, so, yeah, but how do you know that they add up to constant? Okay, I mean, the way you imagine it that fs is much lower than that bandwidth. I mean, that where it becomes half, where it becomes 2 kTr, that is 1 by 2 pi RC, right? That's the bandwidth of the low pass filter, and the way I've shown it, it's probably like 4 times smaller than that or something. You just assume something a lot smaller. So, it is true, of course they will overlap, and it's also true that, so there will be overlap, but it's easier to reason this out in the time domain, okay, at least when fs is much smaller than the bandwidth, okay. So the autocorrelate, the spectral density was the two-sided spectral density. Okay. What is the, this is, let's say, the spectral density, power spectral density. What is the autocorrelation function corresponding to this? Do you know? I mean, what is the, this is of the form, okay, if you are more comfortable. Huh? What's that? Yeah, what, I mean, you don't remember the expression, it's one of those standard things, right? It is? Cos? Exponential? Convolution. So how did we get this after all? This one is some noise passing through a low pass filter, right? That's how we got this. Okay. Now, this has a certain impulse response h of t. Okay. So we passed white noise 2kTr through some transfer function. Okay. And we got a spectral density of 2kTr times magnitude squared of h, which is basically okay. So this is the spectral density. So now I won't prove this, you can show that. In terms of autocorrelation, what is the autocorrelation of white noise? 2kTr delta of f. Okay. And this multiplication in the time domain, what is this? Convolution. What is it getting convolved by? What is the h of f it corresponds to an impulse response of the filter, right? It's a Fourier transform. H star of f, h of minus t, right? So what is this now? H of t, convolution of h of t and h of minus t. I mean, there is some name for it, right? What is that? It is the autocorrelation of that energy signal, right? The autocorrelation of the impulse response of the filter. So basically, and h of t, what is h of t corresponding to this? With scaling factor, what is it? What are the dimensions of impulse response? What are the dimensions of an impulse? Frequency. Okay, because if you integrate this with respect to time, if t is time, this should become 1. So this is something that you should keep in mind also. So h of t, what do you get? It is basically, I mean, you can invert this, so it is 1 by Cr exponential minus t by Rc. And if you, what is the autocorrelation corresponding to this? Forget the scaling, just let me know the shape. Yeah, it will be this, right? First of all, this autocorrelation will always be symmetric. Okay, so it will be like this. So now, this will be of the form yes. I mean, it's there in the handout, so you can take. So exponential minus absolute value of t by Rc. Okay. So essentially, this means that the autocorrelation looks like this. Okay. Does this make sense? The autocorrelation of white noise is just this. Okay. When it goes through a low pass filter, it becomes that. Does this the result make sense? The low pass filter kind of averages and spreads it out. So if you look at very short time separations, that's what this is, right? This tau is time separation between samples, between values. They are correlated, okay, because the low pass filter doesn't allow the output to change rapidly, okay. But if you, for large time separations, that correlation is lost, okay. So that's what it means. Is this okay? So this is what happens. If you low pass filter it, essentially that means that it becomes correlated, and if you low pass filter to a smaller bandwidth, this will expand, right? So that means that it will get correlated for longer and longer time scales. Okay? Is this fine? And if the bandwidth is really small, so that means that the output cannot change rapidly, right? the output will remain the same, roughly speaking, for a long time. So it will be correlated for a long time. So now, so again you think of this sampling of noise. How is the autocorrelation of this discrete time noise related to the autocorrelation of the continuous time noise process? That is of course, but what about the autocorrelation function? What's it? It will be samples, right? It will be samples of that autocorrelation. Okay. So now it's easier to see here. What happens is if you sample this at a high frequency, so meaning you take samples that are closely spaced, the discrete time one will also be correlated. But if you take samples that are spaced very far apart, you take here, there and so on, what do you expect, what has happened to the correlation? What kind of spectral density does this correspond to now? It is white, because it's just the samples are no longer correlated. That is, the low pass filter preserves the correlation for some time scales, but if you sample at time intervals that are much longer than that, the correlation is lost and it becomes white. This is just another way of thinking about it. Of course, that replication stuff is true, but this is easy to think about also. So if you, the bottom line is, if you sample like this, so let's say the maybe I'll show it even wider bandwidth. The spectral density, I mean now I'll show the one-sided spectral density. This is 4 kTr. This is 1 by 2 pi RC. So this is what it looks like, right? This is the spectral density of the continuous time signal. Now I sample it at this sampling frequency, right? Let's say, okay. So this means that for the discrete time signal, I need to specify the spectral density up to Fs by 2. We already established that if the sampling rate is much smaller than the bandwidth, it will be white, okay. And what will be the level here? How do you, so what is the variance here? This is kT by C. What's the variance here? This is also kT by C. So what is this spectral density? Two kT by Fs times C. Okay. So this will of course be larger than that one. I mean this you could imagine also from the spectral replicas, right? They all get added up, because this roughly speaking, if the sampling rate is like n times smaller than this, n replicas will get added up here, right? So this will go up. That's what you expect, and you can calculate exactly also. We assumed it to be white and it will be like that. Okay. So the lower the sampling rate you have, the spectral density value will be higher. Okay. The integrated value will be the same. Is this okay? So this kind of calculations many times you may have to do. Okay. So sometimes there is directly the sampling of a signal, and there will be sometimes some other processes which are equivalent to sampling. Okay. So is this clear? And this, of course, I took it for the particular example. This spectral density, I have shown it for the output spectral density of a first order RC filter, but the same applies to any low pass type function. Okay. So the bottom line is, if you sample at a rate that is much smaller than the bandwidth of the noise, the result tends to be white noise. Okay. The resulting samples will be white, and the spectral density you calculate by knowing the variance, because however you sample, the variance of the sample signal and the variance of the continuous time signal are the same. Okay. Any questions? Any questions about any of this stuff? So now we looked at one type of error. So we said that basically when you transmit data and then you have a clock accompanying the data, something like this. You send this to the data input of a flip-flop and you give this to clock, okay? And the reason we get bit errors is somehow some noise gets added to the signal. Now there is another thing that can happen, that this clock, either when it's generated or finally when it comes to the receiver, these edges can move in the x direction, okay? Ideally, if all these edges should be exactly periodic and their location should not move, okay? But it turns out if you look at a real clock, just like you will have noise, you will have what is known as jitter. These things will be jittering around, okay? And for random noise also, that will have some Gaussian type distribution, okay? The location of the edge will have a Gaussian type distribution. Is this okay? So now what happens due to this rising edge should be sampling here, okay? And then unfortunately the location of that edge can move in either direction, okay? So what can happen because of this? So essentially instead of sampling within this interval, you can end up sampling either here or over there, okay? Is this clear? And let's say this phenomenon, the edge of the clock not being exactly periodic but moving away from the exact location, that movement is known as jitter, okay? There are different kinds of jitter, just like that there are different kinds of disturbances in voltage. You can have sinusoidal disturbances or other deterministic disturbances, and you can also have random disturbances. Similarly here you can have different types of jitter. Now we will again look at this random jitter which has a Gaussian distribution, okay? And the standard deviation of that, it is specified by the standard deviation again as all the random quantities. It is known as sigma j, okay? Is this fine? So now what is the result of this? Can you have errors because of this? So what is the probability of error? So let's say this bit interval is Ts, okay? So now how do you compute the probability of error? Okay. So what is it? So the probability of this edge going off to the right side, to the wrong bit interval is how much? Q of Ts by 2 divided by sigma j, okay? And similarly, it going off to the left and to the wrong bit interval is Q of minus Ts by 2 by sigma j, okay? These two are the same, but whatever it is, then what is the probability of error? Huh? Yeah. So basically, it is probability of going off to the right to the wrong bit interval and that bit being different from this one, right? If it's the same, there is no issue. And how much is that? What do you expect that to be? Half, okay? So half, and then similarly going off to the left and the left bit being different from, previous bit being different from the current bit, so plus half. So again the result turns out to be quite simple. It is this, okay? Yeah, I mean, this thing is a rapidly falling off function, right? So we'll only consider the adjacent ones, not the one after that. You're talking about going off 2 bits to the right side. Yeah. No, so in this case it will be correlated. It's not that these edge movements, right, they cannot be independent. It can't be that this moves forward and that moves back, then there will be no edge. I mean, if you look at it, these edge movements will be correlated. Okay. So that means that if this moves to the right, the other one also will probably move to the right, but maybe by a slightly different amount and so on. Okay. Is that your question? Yeah. So it will move. Yeah. They will keep, I mean, the whole thing will kind of move. For every bit there will be an error, right? There could be an error. Depends on the.
Now one error depends on the other. If one error happens,
Yeah.
the probability of other error happening is kind of increases for an aspect.
No. Per bit this is the error, right? I mean, that is, you want to calculate, let's say for, you want to decode this particular bit, and then what is the probability of error? It will go. I mean, what you are probably referring to is that maybe a bunch of bits will be in error together, and then after that a bunch of them will be clean. But that's okay. The probability is still the what we calculated. Okay. You are talking about, I think, bunching of errors. It's that okay, this goes there, and then you get an error, and maybe like few of them will be in error and so on. Yeah, it will be correlated because the edge movements will be correlated. Okay. Yeah, so we'll, so that's what we'll do next. We'll see how the jitter is specified. So, yeah, there are different ways to specify jitter, but yeah, essentially every clock, essentially the relevant part of the clock is the edge position, and the location of the edge position is different from ideal. So that is jitter, okay? No, what I mean is, it may not be likely that this edge goes off to the right and then the next one is, so that depends on essentially whether the jitter is, now we are talking about whether the jitter is a low frequency or a high frequency process. It's a very high frequency one, then this can be off to the right, but the next one can still be there or have very little movement. If it's a very low frequency one, that means that if this moves out to the right, next one also moves out to the right by almost the same amount. Okay, that's the meaning of low frequency, right? Is this okay? So what we'll do next is look at what the spectrum of a jittery signal looks like, jittered signal looks like. Okay. So these are TS by 2 intervals for making the drawing easy. I'll show it like that, or maybe let me just show it to you. This is better. So this is TS, 2 TS, 3 TS, and so on. Now I'll assume a square wave. This is the clock, right? This is what the clock is. Okay. And what is a jittery clock? So let me just for argument's sake assume that the first edge comes at the right position, and after that there could be movements. Maybe this one will come earlier, the next one will come later, next one will come even more later, and this is a little later, and this is earlier, and so on. It can be in any which way. Okay. Now, the black one is the ideal clock, the red one is the jittery clock. Okay. Now in every cycle there will be two edges. This is true for any simple periodic signal, right? So you have the rising and the falling edges. So I will count those things. Essentially This is 0, 1, 2, 3. Essentially, I will take the normalized value to Ts by 2. Okay. So, at every one of these edges is displaced by a certain amount. Okay. And I call this, let's say, tau 1, tau 2 and so on. This is the jitter. Jitter of kth edge is tau k, and let's say I also define it precisely, like jitter means actual edge position minus ideal edge position. Okay. So that means that actually if in the first case the actual edge appears earlier than that one, so this tau is negative. Okay, and so on. Is this fine? So now one thing you see is this jitter is inherently a sample process. Okay, because essentially you can measure the timing of the signal or the phase of the signal only at the edges. When at the zero crossings you can see, like when the actual one is crossing 0, when the ideal one is crossing 0, and the difference is the jitter. Now clearly the jitter is a sample process. You can only tell at each edge where, like, what the jitter value is. I mean, there is no point in defining it for some time over there. Is this okay? So this is also one reason why you need to know something about sampled random processes. Okay. Now what is it that we will do? We will look at the error or the difference between these two. Okay. So first of all, we have the ideal clock. What will be the power spectral density of the ideal clock? Really? So I have a periodic square wave with a period of Ts and an amplitude of Vp, let's say Vp and minus Vp. Okay. So what will be the impulse? Huh? Periodic impulse. It will have? Yeah, that's okay. So what is this? I think this is what kind of signal is this? This is a square wave. What is the Fourier series of a square wave? Huh? Its Fourier series is not thinking what? Or what is the Fourier transform of a square wave? Bunch of impulses, right? So the power spectral density of this is a bunch of impulses. Okay. So here, I mean, I am talking about power spectral density of a deterministic signal. This is not a random signal. Okay. But you can so what frequency components will it have? Only the odd harmonics. It will not have 0 the way I have defined it. So it will have Fs, nothing will be there at 2Fs, 3Fs and so on. Okay. Fine. And what will be the values? Will they all be the same? No. Okay, you'll have something here and something there and something here and something there and so on. Okay. What will be the strength of each of these things? One by? Yeah, I know, but I want the area of this impulse. I mean, the square wave I have is going between Vp and minus Vp. So I want everything right, all the scaling factors, everything correct for this. How would you calculate this? I mean, let's say we'll concentrate on the components at Fs. I think if you know this, you will know that, right? How much will that be? If this is the power spectral density. Okay. So if this is some value, how is the 3fs component related to that? It will be 1 by 9, because I mean the amplitude will be 1/3 and the power will be 1/9. So let's focus only on this, the component set plus and minus fs. What is the strength of this impulse? Four Vp square by? Okay, how do you get that? So this is a square wave with a amplitude of Vp. Okay, so I mean that is it goes from plus Vp to minus Vp. If I sketch the fundamental component over this, what will that look like? 2 Vp by pi. If I sketch a sinusoid of 2 Vp by pi with the same zero crossings, it will look like this. Yeah, it will be more than that. You might have seen this picture, right? So the fundamental of a square wave will have a slightly higher amplitude, and this is 4 Vp by pi. And in fact, the third harmonic will be like this. So what is the net effect is to kind of raise this part and then lower this part and get it closer to the square wave. Okay, but let's look at only the fundamental. So what is the mean square value of this? This fundamental sinusoid? Mean square value of this? Half of 4 Vp by pi square. So this is the mean square value. Now how is the mean square value related to the spectral density I am drawing? Where is this? So basically the strength of each impulse, I mean this is a two-sided spectral density. So if it was a one-sided spectral density, what would I do? This the strength of this, the area of this impulse will be this mean square value. Now I have a two-sided spectral density, so I have to split it halfway between these two. Okay. So again, like quite simple, you can probably look this up, but you should be able to calculate. Huh? What's that? The Fourier transform, the square of the Fourier transform is the energy spectral density for a finite energy signal. This is a power signal, right? So you can't use that. You have to use the other definition, right? Let's see if I have it here. I thought I showed the handout someday. I haven't do it. Okay, I think it is shared, so you can look it up. But basically, you can't use that definition for this, right? See, the Fourier transform of a periodic signal or a square wave or any other periodic signal has an impulse. What is the square of that? I mean, it's just a... Huh? No, I'm not asking about Fourier transform of a square of a sine wave. I mean, the square of the Fourier transform of a sine wave. It's not defined, right? So, you can't define the... you can't use that. And that is, I think, anyway clear, because what is the energy of the square wave? It's infinite. Okay, so it's not a convergent measure of that. Okay. Skew is like a DC jitter, right? I mean, if all the edges are moved, if all taus are, I mean, you can think of it like that. It's like a DC jitter. He's asking about the difference between skew and jitter. I mean, skew is also jitter, but all the jitter values are the same. So that means that all edges are skewed to one side. Okay. So before next class, find the difference between these two. Okay. Get a suitable expression for it. And of course, these taus are expected to be small. So make a suitable approximation. It's actually quite obvious. What will be the difference? What does the difference between these two look like? Some approximation to that and an expression. And if you can also calculate the spectral density of that. Okay.